Okay, good afternoon. Welcome to your SETI Institute Colloquium series. My name is Frank Marchis. I'm going to be the host today for this session. First, a random announcement. If one of you forgot this bottle, please stop by to pick it up because it's not mine, and someone most likely from this room forgot it somewhere, so somewhere downstairs. Okay, so let's start with the real colloquium series. So today it's a great pleasure to introduce to you Simone D'Amico. I invited Simone to give this talk at our colloquium series because I've been following his research over the past 5 years. Simone is an assistant professor of aeronautics and astronautics at Stanford University. He's the founder and director of the Space Rendezvous Laboratory. He's a Terman Faculty Fellow of the School of Engineering and Satellite Advisor of the Student Space Initiative. This is the largest Stanford undergrad organization. He holds a PhD in aerospace engineering from the Technical University of Delft in the Netherlands, and he received his bachelor and master degrees from the Politecnico di Milano in Italy. So Simone moved here in 2014, but before that he was working at the DLR, the German Space Operations Center in Munich for 11 years. He gave key contribution to the design, development, and operation of spacecraft formation, flying, and rendezvous missions such as GRACE, TanDEM-X, Prisma, and as well DIOS, Proba, and Firebird. Some of you may know some of those missions and mission concepts. So Simone's current research aims at enabling future distributed space system and unprecedented science and exploration. His efforts lie at the intersection of advanced astrodynamics and space system engineering to meet the tight requirement posed by those novel space architectures. So today Simone will talk about the satellite formation flying for future space science and exploration. Please join me in welcoming Simone.
Thank you, Frank. Thank you, everybody, for being here. Today, I will show how satellite formation flying can help answering fundamental questions of space science and engineering. I will do that by leveraging the experience gained in over 10 years at the German Aerospace Center, co-designing, co-developing satellite formation flying missions such as GRACE, Prisma, TanDEM-X, which are currently operational. And I will, in addition, show new mission concepts which are now under development in my laboratory at Stanford. This is how my presentation is structured. I will, first of all, explain what satellite formation flying is and what is it for. Then I will dive into the astrodynamics of satellite formation flying, which is the key enabler of this technology, and use this background information to introduce two new mission concepts my team is working on as we speak. At the end, I will give a brief outlook of the research efforts we are putting into the validation of sensors and algorithms that are needed for satellite formation flying. So what is satellite formation flying? Allow me to start from a biological inspiration. So these photographs is a bait ball, 25 meters in diameter, formed by mackerel fishes, 20 centimeters in length, that work together to accomplish an objective, otherwise impossible to achieve using a single fish or a single unit of this system. So what is the objective here, specific objective? Is to confuse predators. This behavior is not rare in nature. Look at the rendezvous and mating of birds. Look at large groups of geese flying in V formation during migration. Beside swarms of fishes, look at fin and blue whales. I mean, these beautiful mammals, they build a global navigation and communication network covering the entire planet. Their calls propagate along entire deep ocean basins until they fail below the background noise. So in space system engineering, we can see a similar trend, using more satellites to accomplish an objective otherwise very difficult or impossible to achieve using a single monolithic spacecraft. Let me show a few examples. On the top left here, you see an iconic image of satellite formation plane. This is a photograph of Gemini 7 taken by Gemini 6 in 1965 during the first manned spaceflight rendezvous in human history. What's the situation today? Approaching rendezvous and docking with the International Space Station is commonplace. At the top right, you see an artist's illustration of the Proba-3 formation flying mission under development at the European Space Agency. The goal here is to take images of the corona of the sun with unprecedented resolution. So how do you do that? You place an occulter spacecraft in front of the sun to block the light from the inner disk. You then use a second spacecraft at 100, 200 meter separation from the occulter spacecraft, precisely aligned with the line connecting the sun with the occulter spacecraft down to a centimeter level lateral precision, and use a coronagraph instrument to take those images during this artificial eclipse. The mission is due launch at the end of 2018. At the bottom left, you see a concept under development at NASA Ames Research Center, the EDSN mission. This is a swarm of CubeSat that communicate with one another, sharing data within the network, mimicking a fractionated spacecraft, including even the ground in the loop, which is basically splitting the subcomponents, the subsystem of a spacecraft, collocating them in space so to behave as a unit, a single spacecraft. Other highlight here, this is a constellation, is an illustration, a graphical illustration of the OneWeb constellation. 700 microsatellites placed on 20 different orbital planes at 1,200 kilometers altitude, aiming at a global broadband internet service reaching out to millions of users that don't have broadband internet today. So the trend of distribution, I mentioned CubeSat, I mentioned microsatellite, goes hand in hand with a miniaturization trend. This slide shows the evolution, as I see the evolution today. You know that mass is a synonym of cost when it comes to spaceflight. So the goal is to maximize the functionality per unit mass in order to reduce costs. What's happening today? Well, look on the right side here at conventional spacecraft for high-resolution spatial imagery of the Earth. Single spacecraft, van size, weighing tons, costing hundreds of millions of dollars, used on a customer order basis only. For example, NASA and Digital Globe. And look at what young companies from the Bay Area are doing today. Increasing the functionality per unit mass, building satellites, microsatellite by Skybox imaging 100 kilo weight, or Dove by Planet Labs 5 kilo weight, carrying instruments that are capable of a spatial resolution which is comparable with the one provided by the larger platforms, but at a fraction of the cost due to the capability to pack functionality within a smaller volume and mass using commercial off-the-shelf components and using consumer electronics. What does it mean? It means that you can keep these satellites on all the time. You can deploy a constellation of tens of these satellites and obtain global Earth imagery with spatial resolution, not in real time, but with a very high revisit time, a few hours. So overall, we see the rising of distributed space system, what we call a system composed of two or more satellites that work together to accomplish an objective impossible using a single spacecraft. And we classify distributed space system according to the intersatellite distance between the units building the distributed space system and the navigation accuracy which is how well do we need to know and control the motion of these units relative to one another in order to accomplish the objective. So on one hand of the spectrum, you see constellations. Global coverage, very rare orbit control maneuvers. A Galileo satellite, for example, is controlled once a year or so. At the opposite end of the spectrum, rendezvous and docking. Local, virtually zero separation with a centimeter to millimeter level navigation accuracy required. What's in between? Spacecraft formation flying. It's more of a gray zone, depending on the functioning principle of the instrument, of the distributed instrument. We have different requirements in terms of intersatellite distance between the units building the distributed space system and the navigational accuracy. This presentation focuses on satellite formation flying. In particular, I'd like to start from a study I conducted last year for NASA, the NASA grant, to address systematically what are the possible applications of satellite formation flying, what are the breakthrough applications of satellite formation flying. And we have identified three main areas where we expect a game changer in astronomy and astrophysics. Satellite formation flying can be used to measure and characterize gravitational waves as never done before. It can be used to directly image the star vicinity, exozodiacal planet, exozodiacal dust, and exoplanets. In the Earth and planetary science domain, satellite formation flying can be used to build three-dimensional models of the surface of a planet or digital elevation models. It can be used to recover the time-varying gravity field of a planet with unprecedented accuracy. And finally, in the technology and exploration domain, satellite formation flying can be used, or its techniques can be used to build larger structures in space. It can be used to approach repair, to even prolong the lifetime of space assets. It can be used to remove space debris. But let's have a look at a few specific examples. Astronomy and astrophysics. One of the key questions is, how do we measure, so detect, measure, and characterize gravitational waves at frequencies below 1 Hertz? The state of the art is represented by LIGO. It's a ground observatory. It's an L-shaped laser interferometer measuring continuously the relative length of 5 kilometers long arms of the laser interferometer in order to measure gravitational waves with frequencies of hundreds of hertz. Astrophysics is interested in deploying such an observatory in space, in a pristine environment, in order to be able to recover geophysical astrophysical processes like impact of massive black holes, which produce gravitational waves at frequencies below 1 Hertz. How do you do that? You place it in a pristine environment, for example, at the Lagrange points. You increase the arms of the laser interferometer to millions of kilometers, and you place at the end of these arms a drag-free satellite. So how do we get there? Well, at Stanford, we are working on a drag-free satellite on a microsatellite, so 100 kilo class and less, the modular gravitational reference sensor. And we show that it's feasible to achieve a drag-free performance of 10 to the power of minus 12 meters per square second using microsatellite technology. What is a drag-free satellite? Well, it consists of a test mass that is supposed to fly a geodesic trajectory, only driven by gravitational forces. How do you do that? You shield it with the actual spacecraft, you isolate it, and then you use a low-thrust propulsion system to counteract the external disturbances, so to follow that trajectory and then back out the gravitational field that actually caused that trajectory. Astronomy. What is a key question today? Very hot topic. How do we directly image the star vicinity? How do we directly image Earth-like planets? The state of the art is represented by Space Telescope as Kepler. Using indirect methods, we have been able to detect thousands of exoplanets. We are not able to image those. Indirect methods rely on the effect of the planets on the host star, motion, brightness. The idea is to use a star shade to block the light from the star and leave unaffected the light coming from the star vicinity that reaches a telescope, a conventional telescope, that flies in the deep shadow generated, casted by the star shade. How do we get there? That's a new world observer concept of NASA. Well, at Stanford, we are proposing a miniaturized distributed occulter telescope, relying again on microsatellite technology, ejecting a CubeSat from the microsatellite in Earth orbit at a very small cost, and we claim that we are able to obtain 9 to 10's order of magnitude of suppression of light, at least in the ultraviolet spectrum, and image exozodiacal dusk and large exoplanets about distant stars. I will touch upon this concept throughout the presentation, but let me mention the final example here, which is for planetary science. What is the interest today? Well, we want to characterize planets, moons of the solar system. We want to recover geophysical processes happening in these planets. We want to build three-dimensional models of these celestial objects. Look at the comparison between what the Cassini orbiter managed to do about the Saturn's moon Titan, monostatic synthetic aperture radar with a kilometer-level resolution, partial mapping of the moon, and look at what TanDEM-X, bistatic synthetic aperture radar, using 2 spacecraft carrying an identical synthetic aperture radar illuminating the same scene and recovering from the difference of phase measurements the height of the terrain to meter-level accuracy. Can we do that about other planets? Well, there is a recent concept we are looking at from Politecnico di Milano, which aims at a global high-resolution mapping of Titan with a focus at the polar lakes more accurately than Cassini-Huygens with 1 order of magnitude higher resolution. How do we get there? How do we fulfill these objectives? We need to understand how satellites move relative to one another. Because in order to accomplish the objectives of satellite formation flying, we need to build a baseline. We need to build a relative position between these satellites. How do they move in space? This is what I call relative astrodynamics. It's the magic behind the scene. It's the enabler of this technology. So we start with a crash course first through absolute astrodynamics, which is the study of the motion of an object, a space object, for example, a satellite, in a 2-body problem, subject to a Newtonian 1/distance-squared gravity field. We describe the trajectory using a position and velocity vector in the Earth-centered inertial frame. And then we realize that the state, position and velocity, is governed by the fundamental orbital differential equations, nonlinear equations which admit a closed-form solution, which is a conic section. Now, nice, easy, but there are limitations. So this approach cannot handle or can hardly handle perturbations acting on the spacecraft in closed form. What do we do that? We introduce a change of variables. So instead of using position and velocity, we use the integration constants of the original fundamental orbital differential equations, which now are slowly time varying in the presence of perturbations. Now, these are orbit elements. The orbit elements, semi-major axis and eccentricity, describes the size and shape of the orbit. The semi-major axis gives the specific mechanical energy of the orbit. We have then 3 angles describing the orientation of the orbit in inertial space, so the location of the periapsis, the point of closest approach to the primary body, and inclination and right ascension of the ascending node. And the 6th and last parameter is the phasing of the spacecraft along its trajectory, which we call either anomaly or argument of latitude, depending on the 0 reference line that we use. Now, this new state is governed by a different set of differential equations. These are the variational equations developed by Gauss and Lagrange, which now can be solved either analytically or semi-analytically to include all the perturbations of interest. For example, third bodies from Sun and Moon, geopotential of the Earth, which is not a spherical mass distribution, for example, Earth oblateness, J2 effects, drag and solar radiation pressure as non-conservative forces acting on the spacecraft, and intentional forces caused by a propulsion system. Now, this approach has led to very powerful semi-analytical propagators. Here I show as an example the simplified general perturbation theory and the Draper satellite theory, which allows, with a very small computational cost, to obtain a good propagation accuracy. In addition, they provide insight into the dynamics, and they can be used for orbit design. Now, let's rewind and look at how we approach instead the relative astrodynamics problem. In this case, we have two spacecraft. We are in the framework of the two-body problem. One of the spacecraft, we say it's a reference spacecraft with a co-moving orbital frame which is not inertial, with origin at the center of mass of the spacecraft and aligned with a position vector, radial direction, with the angular momentum vector of the orbit, a cross-track or normal direction, and completing the right-handed triad, a third axis we call tangential. And then we describe the motion of a second spacecraft in this moving orbital frame through a state, which is a relative position and a relative velocity. Now, this state is governed by a combination of the fundamental orbital differential equations I spoke about before. For small separation between the spacecraft as compared with the distance from the center of mass of the Earth, these equations simplify to linear Loden and Chauner-Hempel equations which admit closed-form solutions. For example, the most popular one is the Yamanaka-Ankersen closed-form solution. Now, this approach has the same limitations that we have observed in the absolute astrodynamics case. We can hardly include perturbations in formation flying. So what do? Change of state. Instead of using relative position and velocity, we use combinations of orbit elements, which basically reflect a difference in angular momentum vector between the orbit, a difference between eccentricity vector between the orbit, a difference in specific mechanical energy, or semi-major axis between the orbit, and the phase relative to one another of the spacecraft along their trajectory. So this method for small separation can lead to impressive results. For example, here you see a linear propagation of so-called relative orbit elements when we include perturbations caused by Earth oblateness effects, J2, differential drag, and obviously Keplerian dynamics. So the formation is described by 3 points that you see here in the phase space, which are slowly moving in the presence of perturbations. The relative eccentricity vector draws a circle. It has a phase called theta when affected by J2 effects. The relative inclination vector draws a vertical line affected by J2 effects with a phase given by phi. This speed is proportional to the x component of the relative inclination vector, or to the difference in inclination between the spacecraft orbits. And so we can decide to align the relative inclination vector with the y-axis, so to remove Earth oblatency effects on the relative inclination vector. Finally, a third point is given by coordinates given by a relative semi-major axis and a relative mean longitude, or the relative phase between the spacecraft. This is driven by Keplerian dynamics, obviously. So if we have a difference in mechanical energy between the two spacecraft orbits, we have an unbounded motion and a drift between the spacecraft identified by this horizontal line. In the presence of differential drag driven by the differential ballistic coefficient between the spacecraft, we have a drift linear of the relative semi-major axis, which provides a parabolic motion of this point. Overall, we have a simple geometrical representation of how the relative dynamics is evolving over time in the presence of perturbations. And this can be used for formation flying design. It can be used for maneuver planning. For example, we can place control windows about these points in order to efficiently keep the formation at some prescribed nominal relative orbit elements. But now, how do we go back to the actual baseline between the spacecraft? How do we map back relative orbit elements to relative position and velocity? Well, let's consider a spacecraft at a certain phase angle. I call it u. That's our independent variable. It's like a time. It's a phase angle 0 at the equator, called argument of latitude. And we pick our radial, along-track, cross-track, co-moving orbital frame. What does this reference spacecraft sees in the co-moving orbital frame? Well, for small separation and the small eccentricity, the trajectory, it's a relative orbit, drawn by the deputy spacecraft is a section of an elliptic cylinder. That's a dual of the conic section for absolute astrodynamics. So in the plane, the orbit plane of the reference spacecraft, which is aligned with radial and along-track direction, the deputy draws a 2x1 ellipse whose size is driven by the length of the relative eccentricity vector. And in the plane perpendicular to the flight direction, the deputy spacecraft draws a tilted ellipse with size driven by the length of the relative eccentricity and inclination vectors. And the tilt and squeeze of this ellipse are driven by the angle between the relative eccentricity and relative inclination vectors. So what we can do is, first of all, try to shape our relative orbit by picking appropriate initial conditions or picking appropriate relative orbit elements. First, removing the difference in semi-major axis. This removes the drift of the formation. Second, picking parallel relative eccentricity inclination vectors. This provides an ellipse in the plane perpendicular to the flight direction. This is called EI vector separation, which is used in many missions to guarantee safety at all times. In particular, this ellipse ensures that there is always a minimum separation perpendicular to the flight direction between the spacecraft, irrespective of uncertainties in a long-track direction, which is where the dynamic coupling happens. So basically, you have to imagine a deputy spacecraft following an helicoidal motion about the service spacecraft, never colliding with it. We then pick theta and phi, those phase angles of the relative eccentricity and inclination vector, such that they are not only parallel, but also aligned with the y direction of the phase space. In such a way, we remove J2 effects from the relative inclination vector. And on top of passive safety, we get also passive stability of the formation. Third, look at the independent variable. The deputy spacecraft location along the relative trajectory depends on the location of the servicer spacecraft, u, along the absolute trajectory. So this means that we are able to build the desired baseline between the spacecraft at a desired location with respect to the primary body. So we obtain a baseline which is latitude dependent. An example, this is the TanDEM-X nominal formation with a phase of the relative inclination vector and an eccentricity vector at 90 degrees. When u equals 90 degrees, which means when the formation is at the northern extreme latitudes over the poles, the deputy spacecraft is below the reference. When we are at the equator, instead, the deputy spacecraft is on the n-axis. This can be used to obtain an horizontal baseline for cross-track interferometry at the equator, and can be used to obtain a vertical baseline for cross-track interferometry over the poles. And by changing the phase of the relative eccentricity and inclination vectors, we can scan the complete planet by having the maximum baseline basically moving across all latitudes. Note that for synthetic aperture radar interferometry, what counts is what's so-called the effective baseline, which is the distance between the spacecraft or a relative position in the plane perpendicular to the flight direction and perpendicular to the line of sight. So we are now extending this concept to orbits of arbitrary eccentricity. In this case, if we are able to properly reformulate the relative eccentricity, the relative orbit elements, we obtain a relative orbit which is again a section of a elliptic cylinder. But in addition, superimposed, we have a second mode, which is here identified by the red color, which is flown twice per orbit, and it's proportional in amplitude to the eccentricity of the reference orbit. So this is just to say that research is going forward in trying to extend this methodology to orbits of arbitrary eccentricity in order to design formations. And we have been able so far to include not only Earth oblateness effects and differential drag effects on formation dynamics in orbits of arbitrary eccentricity, but also solar radiation pressure, third-body perturbations, and so forth. This gives an idea of the difference between a near-circular orbit case and a highly eccentric case. Earth oblateness effects and differential drag are causing perturbations of the relative eccentricity vector, which are perpendicular to the absolute eccentricity vector or parallel. Again, geometric insight. So now, how do we use this insight into dynamics in order to control the relative motion, which is at the end our objective? Well, we look at the variational equations, Gauss and Lagrange, and we find out that in order to change the relative orbit elements, we can do that with a minimum propellant consumption or a minimum delta V consumption if we minimize the path in the relative orbit element space. So we translate an optimization problem, which is in fuel consumption, in delta V, we translate it to a minimum path problem in the space of these new variables. So what we do, we are able to find closed-form solutions for control. You will see them in action later when I address the mission concept. By splitting the problem into two parts, a global part, guidance problem, and a local part, control problem. The guidance problem seeks M-intermediate configurations or jumps of the relative orbit elements, including perturbations over a long interval from an initial to a final condition. Once we know the jumps of the relative orbit elements or the trajectory in the 6D space, we can define a control problem which seeks a finite number of maneuvers, P, maneuver size and location, which accomplish that change of relative orbit elements over a short time interval where we can ignore perturbations. Now, we can set up convex functional to be minimized in order to minimize the propellant consumption and find through the application of optimality conditions a unique solution for the guidance problem. It basically reduces to a linear system. And for the control problem, the linear system that we get is decoupled in out-of-plane and in-plane relative motion control. In particular, we find that one cross-track maneuvers is necessary and sufficient to control the relative motion out of plane. Instead, for the in-plane relative motion control problems, in the presence of two and more maneuvers, the problem is overdetermined. So we can use the excess degrees of freedom in order to minimize the delta V using trains of pairs or triplets of maneuvers which minimize the propellant consumption in closed form. So let's, after this compact crash course in relative astrodynamics, let's see how we apply it to actual missions. I will describe first some flight results from the TanDEM-X mission, and then introduce the two new mission concepts we are developing at Stanford. TanDEM-X. So TanDEM-X stands for a TerraSAR-X add-on for digital elevation measurements. A formation of two quasi-identical spacecraft carrying a synthetic aperture radar. The formation was formed in 2010 with the goal to build a digital elevation model of the Earth or reconstructed three-dimensional surface of the Earth, in particular the height elevation down to 2 to 4 meters resolution, depending on the slope of the terrain, globally. This is not available today. How is this done? Well, the German Aerospace Center, which is the lead of this mission, has developed a concept based on cross-track interferometry. Basically, you take SAR images of the same scene, you subtract the phase measurements from SAR, and you recover the height elevation from this difference of phase measurements with an error that is proportional to the effective baseline I was describing before. The baseline is mainly in the plane perpendicular to the flight direction, so in cross-track direction. 200 to 600 meters baselines between the two spacecraft, dependent on the latitude, with a control accuracy requirement which is about 20 meters for the cross-track direction and 100 meters for the along-track direction. Not so aggressive, not so demanding. Now, thanks to the fact that TanDEM-X is able to produce a large effective baseline and varying over latitudes, it's able to achieve basically a 1 order of magnitude improvement on previous approaches, such as the shuttle radar topography mission, which use a second radar at the end effect of a robotic arm, which is only 40 meters in length. So it's a limited baseline available. The secondary objective of TanDEM-X is a long-track interferometry. In this case, the baseline is mainly in a long-track direction. Phase measurements are differenced between radars that are mainly separated in a long-track direction. And through the Doppler shift, you can recover velocity maps of on-ground objects. You can recover the velocity of slowly moving vehicles, cars, ships. You can use it for oceanography, currents, glacier movements. But what is the difficulty for a long-track interferometry? The baseline is shorter. We are at 40 meter separation in the X band, which is the frequency used by TanDEM-X, and the control accuracy is at 10 meters, something that is hardly achievable from ground. So this motivates the TanDEM-X autonomous formation flying system that I co-developed at DLR. Here you see an architecture consisting of a ground segment, TerraSAR-X and TanDEM-X, a space segment. The TerraSAR-X spacecraft is sending through an S-band intersatellite link GPS navigation solution from a single frequency receiver available on TerraSAR-X to TanDEM-X. TanDEM-X gets its local GPS navigation solution and the one from TerraSAR-X every 10 seconds and implement an extended Kalman filter to estimate the relative orbit elements of the formation. The relative orbit elements are then fed into a formation control module, which does maneuver planning in closed form through pairs of maneuvers, providing minimal delta V. And the commands are sent to a cold gas propulsion system that implements the maneuver for formation control, autonomously on board. That's the first scientific mission in human history that used autonomy to accomplish a scientific objective. This chart summarizes flight results from TAFF. This is a campaign of 12 days where DLR has been exercising different control periods for the maneuver pairs in velocity and anti-velocity direction. Vertical dashed lines represent the maneuver pairs. Red vertical dashed line represents instead absolute orbit control maneuvers sent from the ground in order to keep the mean altitude of the formation throughout the mission. These are 1 order of magnitude larger than the tiny maneuvers necessary for relative motion control. The green line represents the desired relative orbit elements, in particular a difference in semi-major axis, the phase of the relative eccentricity vector, and a relative phase or mean along-track separation between the spacecraft. The pairs of maneuvers keep the relative orbit elements confined within the desired control windows with an accuracy of 10 meters as required by a long-track interferometry. This performance is quite remarkable if you compare it with what the ground would be able to do, and if you also see the predictability of the system. Imagine that on ground it's possible to predict the location time of the maneuvers performed by TAFF with a minute level accuracy over 2 weeks. And this simplifies enormously operations and mission planning. Now, this is present. Can we use this knowledge for future missions? Well, I'll address quickly two mission concepts. The first one is to map Titan. Why Titan? Well, Titan is the second largest moon of the solar system. Titan is the only moon which has a dense nitrogen-rich atmosphere in the solar system. And it has a meteorological cycle where methane basically behaves like water on Earth. It is the only celestial body besides Earth with surface liquid lakes. So there is a strong interest to understand Titan. And what we have today is what Cassini did. 170 flybys of Titan managed to a monostatic synthetic aperture radar to do a partial mapping of Titan with an accuracy at the kilometer level. Well, this new concept originated from Politecnico di Milano, relies on formation flying to obtain a global mapping of Titan with a focus on the polar lakes with a meter level resolution instead. How do we do that? First thing first, we look at the environment. What happens in terms of relative dynamics about Titan? We have a much denser atmosphere, something like 3 times the atmosphere on Earth at the same altitude, which is transparent anyway to Ku band, which is the frequency used by this mission. We have third body effects which are 10,000 times larger than the third body effects about the Earth. So basically, Saturn is driving the differential acceleration acting on the formation. J2 effects, marginal, negligible. So what happens if we propagate the relative motion of a formation about Titan and we probably select the initial conditions? We see here the relative eccentricity vector, the relative inclination vector from 0 to 100 days, and the relative eccentricity vector from 0 to 100 days. A proper choice of the initial condition can guarantee an anti-parallelism or parallelism of the relative eccentricity and inclination vectors, thus guaranteeing passive safety. And it can be used to look at the phase angle of these vectors to build an horizontal baseline, so maximum crosstrack over the poles where it's most needed, and a vertical baseline instead over the equators. Now, this is limiting in the sense that we want a global mapping of Titan. How can we do that? We use the dynamics. How? We perform sparse pairs of maneuvers every 20 days, and we enforce a motion of the relative eccentricity and inclination vector you see circular, exploiting the third body effects from Saturn, over 600 days where they are always antiparallel, and where by changing the phase of the relative eccentricity and inclination vector, we are able to scan the body from 25 degrees to 90 degrees latitudes, always ensuring the best effective baseline for cross-track interferometry. Well, the resulting delta V budget is at a few meters per second, well within the capability of current propulsion system. Now, the second and final mission concept, this is under development in my laboratory, is for direct imaging of the star vicinity. Why is it difficult to image the star vicinity? Well, stars are very bright. They are billions of times brighter than the objects orbiting the stars, exoplanets, exoterical dust, for example. Imagine if we were able to suppress the light from the star. So we would be able to see the planet orbiting the star. Depending on the target, we need to suppress light from 6 to 10 degrees of freedom. Exoterical dust versus Earth-like planets. How can we do that? Well, the most promising concept is a star shade. A star shade is a precisely manufactured, properly shaped shade that blocks the light from the star, suppresses the light of the star up to tens of the magnitudes, generating a deep shadow where you can place a telescope, a conventional telescope, which then can observe the targets of interest orbiting the star. Now, this is not easy. So in order to suppress light, you need very large star shades with a proper sizing. Here we are speaking about tens of meters for current NASA concepts. In addition, the targets, when you look at the separation of the targets from the host star, we are speaking about hundreds of milliarc seconds. So this means if we combine tens of meters of occulter size, diameter, with hundreds milliarc seconds of, we call it inner working angle, so you get that the telescope has to fly within the shadow of 1-2 meter size at tens of megameters from the occulter. So formation flying has to be compliant with the inner working angle and with the shadow size. This leads to concepts like the New Worlds Observer, which are gigantic and cost billions of dollars. At Stanford, we asked, how small and cheap can an occulter telescope be while still retaining scientific and technological value? And what we did is to conceive mDOT, a miniaturized distributed occulter telescope, which relies on microsatellite and CubeSat technology. Here you see a comparison parameter by parameter between mDOT and the New Worlds Observer. We use a 2 meters diameter occulter, which is hosted on the microsatellite. The telescope aperture is 10 centimeters in the ultraviolet spectrum. It's hosted on a CubeSat that is ejected by the microsatellite in orbit for separations which are hundreds of kilometers. The control precision is 1% of the baseline along the line of sight, and it's 10 centimeters approximately. That's the size of the scientific shadow, lateral to the line of sight. The orbit is a high elliptical orbit with an apogee altitude above 25,000 kilometers. For a budget that is a tiny fraction of the budget of the original mission. But how can we accomplish the objectives of direct imaging using a small platform? Well, the secret here is in optics and orbit design. So for optics, what we do is to reduce the wavelength. Instead of working in the visible spectrum, we work in ultraviolet spectrum. And we are able to demonstrate a capability of suppressed light in the presence of manufacturing errors by 8 to 9 orders of magnitude using such a small star shade, but in the ultraviolet spectrum. The deployment concept for the star shade is extremely simple. So we have petals, which are first deployed, so a la solar panels, so to say. And then we have winglets that complete this petal-shaped so-called apodization function, which is optimized in order to obtain the proper light suppression. Now, assuming that we have solved the light suppression problem, how do we do the formation flying at low cost in Earth orbit? Previous authors did not consider formation flying in Earth orbit because the differential accelerations were considered too large to be compensated by a propulsion system. Well, we conducted an optimal orbit design to find out that it's possible. How? Well, you look at the differential acceleration caused by gravity in a direction of interest, so lateral to the line of sight. And we find that orbit where that differential acceleration is minimized. It turns out that if you align the formation approximately with the angular momentum vector of the reference orbit, then you minimize the differential acceleration. And if you do that over the course of an apogee arc, a couple of hours, you have tolerable delta V consumption, and you can keep that inertial alignment with your target star. You break up the formation after the apogee phase. You use an EI vector separation, as I described before, a passively safe relative motion, and you reconfigure the motion through impulsive maneuvers peaked in a delta V optimal manner in closed form. And you reacquire the formation at the next apogee phase for the next observation arc. You can accumulate hours of integration time by connecting all these science phases. In particular, the delta V that we get, it's quite promising. Look at a launch of opportunity, for example, on SpaceX to a GTO, a geostationary transfer orbit. We are able to achieve tens of hours, 40 hours or so of integration time with a budget of 100 meters per second, which is okay for a microsatellite. It's our cap. What happens if instead we can select the launch? A bit, more expensive. If we have a custom launch, we can pick the eccentricity vector of the reference orbit so to minimize airfoil latency effects on the formation, and then reduce the delta V consumption. In particular, we are able to achieve hundreds of hours, 100 hours of integration time at the same delta V cost if we are able to select the launch. And this would enable to directly image a large exoplanet, for example, about Alpha Centauri. The numbers you see here are a simulation done for a target at Alpha Centauri, but we have been working with other targets, such as Beta Pictoris, Polaris, etc. So I would like to conclude this presentation with a very brief outlook of the research efforts we are putting to validate sensors and algorithms needed for formation flight. Experience tells us that in order to verify the proper performance of your sensors and algorithms in space, you need to stimulate those sensors in a manner that is as realistic as possible, as representative as possible of the actual environment that these sensors are facing in space. Especially here, the focus is on optical navigation. So how do we validate with high fidelity those optical navigation sensors, those cameras that are needed to navigate relative to another spacecraft? Well, one approach that is under development in my laboratory is virtual reality. So we stimulate a spaceborne camera. Here you see a Sinclair Star Tracker obtained through a cooperation with Skybox Imaging, which is exposed to an image rendered on a micro display, an OLED display, a dynamic image. In between, there is corrective optics designed in order to correct, to take into account the actual working distance of the camera. A Star Tracker is focused at infinity, for example. We have been able to calibrate such a device, such an optical stimulator, down to sub-arc seconds accuracy. And this device is deemed vital to verify the behavior of cameras, for example, during the acquisition phase, during the far-range rendezvous phase, in a formation flying scenario. What is the next step? Let's try to stimulate the camera in an actual environment that is physically similar to the environment in space. And this is the robotic testbed we are developing at Stanford, which tries to reproduce the illumination conditions in space with the Atmos reality. It's a PR video that was created for the occasion, by the way, by one of my PhD students. That's our 7 degrees of freedom robotic arm with a sub-millimeter repeatability accuracy, hosting a camera and mimicking a rendezvous trajectory relative to a space-resident object, which is here a CubeSat. We can illuminate the CubeSat, reproducing albedo diffuse light and direct light from the sun using special devices. We use curtains and materials with a very low reflectance coefficient, and we reproduce the space environment. This is just first light we obtained a week ago, but it gives you an idea of the potential of robotic validation for optical navigation today. So thank you very much for the attention, and I'm happy to take questions.
Thank you, Simone. Sorry. So, yeah. Okay, we have time for a few questions. I'm going to start on this side.
Hi, thank you very much. That was really interesting. My question is about the last thing you talked about, the Starshield project. And I mean, it looks really hard, but once you were able to solve the engineering problems and get something like that in space, first is how far a star, how far could you look? Like how far away a target star could be for a practical application of this? Like, is it, you know, 12 light years, 10 light years, 1,000 light years, whatever? And once you did your observations on a particular solar system, could you then use these techniques to reposition the satellite and the star shield and look at a different star? Or is it just one star and that's it for that particular satellite?
Thank you for the question. Well, we can look at 10 digits parsecs. Regarding reconfiguration of the formation, this depends on the mission at hand. For example, missions like a New Worlds Observer or a planned mission with WFIRST, AFTA, they incorporate the capability to reconfigure the formation, to retarget it in order to have a decent scan of the sky. Missions like mDOT I was describing here, so miniaturized, low cost, Earth orbit, they are affected by limitation due to the differential dynamics, so high propellant consumption. So we can at most afford one retargeting from our analysis. For example, if you look at Canopy and Beta Pictoris, these stars are separated by 7 degrees. And there is a very interesting exoterical dust disk about about Beta Pictoris, where planets are even in formation. And so one could use one star, for example, for some calibration purposes, and then retarget, but only by a few degrees, to a second target for the complete mission lifetime. But that's the limitation of an Earth orbiter.
Hello, yeah, great talk, thanks a lot. I have 2 questions. First, regarding the relative astrodynamics. And first, you just give equation just in the position and velocity. And I'm sorry, I cannot remember the name of the equation. My question is, what's the difference of that equation compared just to the conventional Hill equation? I'm sorry. My second question is, and I have some difficulty to transfer from the navigation technology you described for the TAFF just to the Titan exploration system, because my understanding is that TAFF is basically GPS based, but Titan definitely has no GPS, and so maybe would you please just comment on, just speak a little more detail about the navigation system of the Titan exploration?
Very, very good questions, which gives me the opportunity to clarify a couple of aspects. The first question, he yields Clohesy-Wilshire equations. They use relative position and velocity, either Cartesian or curvilinear form, for small separations between the satellites as compared with the distance from the center of the Earth, and in a circular orbit. These are the 2 assumptions. What I was speaking about is a more recent developments. where basically we are able to find an equivalent of the Hickel-Schwicher equations that it's applicable to orbits of arbitrary eccentricity. These are the Lode and Schauner-Hempel equations. They are old, but recently, in the last decade, solutions, closed-form solutions, like the Yamanaka-Anker solution for these equations has been found that are valid for orbits of arbitrary eccentricity. So the key difference is that the linearization is for small separation, but the orbits is arbitrarily eccentric, close, arbitrarily eccentric. Second question, the navigation aspects. So this study I was referring to do not take into account the navigation aspects. To be 100% fair, in order to recover the height of a terrain using synthetic aperture radar interferometry with a desired level of accuracy of TanDEM-X at a meter, 2 to 4 meters vertical resolution, using X-band, you need to know the baseline between the spacecraft, in particular between the face center of the synthetic aperture radars, to a fraction 10 times the wavelength. So we are speaking about below a centimeter, down to a millimeter. In 3D, it's not just the distance, it's the 3D relative position between those. So in Earth orbit, we can do that because we have GPS and we can use fancy carrier phase differential methods in order to achieve that level of accuracy. We know how to do that. About other planets, we don't have GPS. So we'll need to use other techniques, for example, using laser, K-band radars, other metrology devices that are capable of achieving a very good performance in relative positioning, but only 1D. So we'll need to complement those sensors in a way to be able to reproduce the baseline in 3 dimensions. But you're right. I mean, that's.
Yeah, thank you very much for the very profound presentation. Very nice. You touched upon communication networks like the OneWeb and also scientific applications here. I'm wondering, Earth observation, Planet Labs, or also at TanDEM-X, what are the benefits of formation flying, large-scale formation flying for Earth observation?
At the beginning of the presentation, I tried to distinguish between constellation and formation flying. So I am an engineer, fundamentally Cartesian man, so to say, and so I need to put on an X and Y some variables in order to understand where these architectures stand. And so constellation gives global coverage, possibly a very short revisit time. They have very relaxed flight dynamics requirements and can be used for a near, in the future, near real-time updates, high spatial resolution imagery of the Earth. That's constellations. Satellite formation flying is a different cup of tea. In a sense, with satellite formation flying, you have smaller separations, typically, and you try to build a scientific instrument with a longer baseline, longer than what you could do with one spacecraft. A synthetic aperture radar itself is able to achieve a baseline of hundreds of meters just because it's flying at 7 kilometers per second in low Earth orbit, for example. And the train of pulses getting back to the radar builds this synthetic aperture, but only in flight direction. So you add a second spacecraft, you obtain a baseline in cross-ray direction that instead necessary in order to recover the high resolution. Now, your question could go into the direction of saying, can we do a constellation of formation flying satellites? The answer is yes, but what for? And it needs a business case. And do we need that level of resolution with a very short revisit time? So there are questions that one needs to address before starting thinking of formation flying in combination with constellation. Does it answer? Yeah.
So you mentioned that consumable propulsion material was what limits the lifetime of some of these missions. Is it really true that that's the limiting lifetime factor? If you would put something around Cassini in that hard radiation environment, they're very small, not a lot of shielding. What's the reality of that?
Yes, I mean, my cut was from an astrodynamics perspective. I was showing how an optimal orbit design can overcome limitations that sometimes stop researchers to consider certain mission concepts. And with a few meters per second delta V, we are able to map over 600 days the complete surface of Titan. I was not considering the radiation environment, obviously, which is crucial, obviously, for all deep space missions. You're completely right.
Okay. Since we don't have any more questions, I would like Simone to remember his stay here and thank him again for this presentation. So here, a wonderful cup that I hope you're going to use at Stanford University to talk about the great talks you give at SETI Institute. Thank you very much.
Thank you very much. Thank you for the attention. Appreciate it.